video, we are going to discuss a very important stuff in real analysis, that is, our real number system is a complete ordered field. It means, by this I mean that our real number system is satisfy completeness property. By this I mean real number system is a complete ordered field, and real number system is a field. So real number system is a field. By this I mean it satisfies the algebraic properties. The algebraic properties with respect to algebraic properties with respect to addition, with respect to multiplication, as well as it satisfies the distributive property. It means real number system satisfy cumulative property, associative property, identity property, and inverse property with respect to addition as well as with respect to multiplication, and it satisfies the distributive property. And so our real number system is a field. Now our real number system is an ordered field. What does mean by this ordered field? So we are going to first understand what is an ordered set. So ordered set means that there is a relationship between elements of the set. There is a relationship. There is a relation between elements of set, elements of set. What kind of relationship it is? It is the relationship is of three kinds. First is x is less than y. Second is x is greater than y. Third is x is equal to y. If I take any two elements of a real number, let's say x and y belongs to x real number system, then out of these three possibilities, one always satisfies. Out of these three possibilities, one always satisfies. For example, let's say I take 2 and 10. As you know, both are real number system. Exactly, both belongs to a real number system. Both are your real numbers. So you can see that 2 is less than 10. So you can see that this possibility satisfies. Always, you can take, I can bet on that. You can take any real number system. Out of these three possibilities, one always satisfies. One always satisfies. And the second thing is that, order property, if I take three real numbers, then if x is less than y and y is less than z, then always x is less than z. By this I mean, as you can see that 2 is less than 10 and 10 is less than 15. You can see that 2 is also less than 10. Very simple, very simple, and very interesting. So this is the relationship between two real number system is this, and between three real number system is this. And always remember that reordered property means that the order of every element, every element is unique. Means that on real number system, the location of every element is unique. For example, you can see that if I make a real number line for you, this is a real number line. I have 0, I have 1, I have -1, and this is positive numbers here and over negative number here. You can see that over all the positive numbers have very on the right side and over negative number on the left side. So on real number system, the position of 1 is unique. I cannot write in place of 1, 2. Similarly, 2 is here and 3 is here and all the numbers here. So the position of every number on real number system is unique. So this is our ordered property. So on the completeness properties, inshallah, we will discuss in the next video. So this is our first theorem. The theorem we will discuss here in this video. So before we understand this theorem, I want to explain this thing. This is our real number system. And this is our real number line. Yes, real number line. And I take a subset S of real number system. So S is a subset of real numbers. Okay. So all the elements of the x belongs to us. So these are the elements of the x. As set S is this, and small x are all the elements of S. Then always remember that all the elements which are not the element of S but are real numbers on the right side here, always greater than the elements of S, and all the element on the left side of S are less than S. So all the elements, all elements greater than elements of S, element of S are the upper bounds of S. Similarly, all elements less than S, less than elements of S are lower bounds of S. So all the upper bound of S always exists on the right side of S, and lower bound of S will exist on the left side of S. So these are the upper bounds of S. Bound of S, the numbers here and the numbers here, there are the lower bounds of S. Lower bounds of S. I hope you understand this. This is a very, very important thing. Okay, so now we are going to this. Suppose that S is an ordered set. So S is an ordered set. So here we have S. This is our S ordered set. And E is a subset of S. So now we take the subset of X, subset of ES, which is here, let's say. So E is here. Okay. Now there exists a beta which belongs to S. Beta belongs to S. So let's say beta is here, which belongs to S. So this beta is greater than all the elements. So this beta is greater than or equal to all the elements of E. Then E is bounded above and call it the upper bound of E. For example, then as you know that beta is greater than or equal to all the element of E, then this E is called the upper bound of E, and the set E which has upper bound, it means there exists a number with there exists a lot of number greater than that, but I find one number, so that if I found only one number greater than that set elements of the set, then our set itself is called bounded above, and beta is called upper bound of E. So as I found the upper bound of S here, so it means the set S in this example also is bounded above. Similarly, which I think so, I will discuss that in the next video, but I should explain here. If, as you know that the set S has lower bound, then the set is called bounded below. If lower bound exists, then it is bounded below. If upper bound exists, then it is a bounded above. So these are very important things. I hope I will understand it. Thank you so much.